All right, today what we're going to do is we're going to learn about linear versus nonlinear. So the title of this one today is linear versus nonlinear. Okay. We're going to start first by defining linear. Okay. And if we remember way back when we were doing linear equations, we talked about linear is basically has a constant rate of change. So basically what that means, it will change by the same rate over and over and over again, okay? So linear has a constant rate of change. Also, when we look at a linear equation on a graph, it's going to be a straight line, okay? Nonlinear. Nonlinear is just the opposite. Nonlinear are functions whose rate of change is not constant. So rate of change that is not constant. And so what that means is it does not change by the same amount each time, okay? So linear has a constant rate of change, nonlinear rate of change that is not constant. So they're the opposite of one another. So what we're going to first look at is two tables that are linear. So both of these tables that we will look at first are going to be linear tables, all right? I don't know that immediately by looking at it, so what I have to do is I have to do some figuring. So what I do is I go ahead and find the rate of change again. And again, to find the rate of change, I look at the difference between each numbers. So this one, it goes down by 15. This one, it goes down by 15. And this one, it goes down by 15, okay? I then look at the x and I see, okay, well, this is constant over here. So to be linear, this one over here has to be constant. So 2 to 4 means it went up by 2. 4 to 6, it went up by 2. 6 to 8, it went up by 2. So because this constant matches this constant, all right, and is equivalent, this lets me know that this is a linear equation. So I'm going to write down linear. Okay. So let's look at another one. All right, I don't need to move it over. I'm going to look at over here first at what this rate this is changing by. This looks like it's going up by 3 each time. So 6 to 9 went up by 3. So because each of these is constant, in order to be linear, the same exact number needs to appear in each of these three, okay? So when I look at -3 to 9, it went up by 12. So to be linear, this one also would have to go up by 12. And if I do the math real quick, 9 to 21, it does go up by 12. Just to make sure, I'll make sure this one goes up by 12. 21 plus 12 does equal 33. So yes, so this 12 goes with this 3, 12 goes with 3, 12 is equivalent to 3 with the 3. They're all equivalent to each other, so this just lets me know, hey, it's linear. Okay, so that's linear on a table. Notice the same constant rate of change from each, and then over here, x is changing by the same amount. Okay, so let's look at two examples that are non-linear. All right. So in the nonlinear, we're going to go ahead and look over here at the x. Notice that each x is going up by 3. So that's okay. Now we're going to look at this one. From 1 to 16, that went up by 15. From this one, from 16 to 39, it went up by 34. From this one, 49 to 100, it went up by 51. If I take a look, each of these three is different, while these three remain the same. Okay? That gives it away that this is not a linear equation. So I'm going to write nonlinear. So again, it's nonlinear because even though these three stayed the same or constant, these three did not stay constant and they changed each time. All right. As a result, they are not the same or equivalent to one another. Okay. One other example that is nonlinear is this one right here. Again, you can see here that this constant over here is that it went up by 1 each time. So over here, we went from 1 to 3 is a +2. From 3 to 6 is a +3. From 6 to 10 is a +4. Even though that the +1 was constant, over here, these were not constant. They changed. It was 2 one time, 3 one time, and 4 one time. As a result, this would be a nonlinear equation. So hopefully that gives you an idea about what a linear equation looks like in a table and what a linear equation looks like in a graph, or in a nonlinear equation looks in a table.